Sorry we couldn't meet today. I'm going to go ahead and go over your lesson for you anyway, and hopefully it'll be convenient for you because it's recorded and you don't have to tune in live. So, somebody's playing with the dog. All right, so let's go ahead and get started. And let's see. So our lesson today is on gas behavior. And this is in our unit, which we're getting close to the end of, on enthalpy, intermolecular forces, states of matter. And so what we're talking about today, and before we get into the lesson, I forget, let me tell you. So pay close attention to this lesson in the slideshow, because I'm going to be throwing up some random images. And I mean random, they're weird, they're out of place, you'll know. And your job is to post them in the discussion in Teacher Ease in the assignment. And you have to name one of the images. Now, we've not used this feature on Teacher Ease before, but it's called teacher-led discussion. So I have posted the topic, and you all should be able to add your comments to it. So fingers crossed that it works the way I hope it will. So the only catch is you can't name something that someone else has already listed. So if I were you, I'd write notes and write down all the different things you see. There are weird, out of place, random images. That way, if the one that you thought you might post was already posted, you have a backup. And there are more than enough for everybody. So let's talk about gas when pressure is constant. So when your pressure is constant, we can start talking about Charles' law, which says that when the pressure of a gas is constant, if the temperature increases, the volume increases. And then likewise, if the temperature decreases, the volume decreases. So let's think about this hot air balloon here. And I think your book talked about hot air balloons as well. So if you've ever seen a hot air balloon close up, you know that right above the basket, right here, there's a big burner. It's like I think it's like a gas burner, and it makes super hot flames that shoot up into the hot air balloon. Sometimes you can hear them passing over because you hear the whooshing sound of the flames shooting up. So what's happening there is it's heating up all of the air around it, right? And that air goes up into this enclosed space here. So our atmospheric pressure all around is constant. That's not changing. But as we are increasing the temperature of the gas, we end up increasing the volume of that gas. So it gets bigger and bigger until it fills this bag. And then that has to do also with how dense it is. Now it's the same amount of gas that was in there to begin with, but it's more spread out because our volume has increased. So therefore it's less dense, and that actually causes the air around it to push down underneath, which makes the balloon go up. Charles's law, did you catch that? Charles's law. Cole, I'm recording a lesson. I'm recording a lesson. They're cooing at the dog like a nut. Charles's law says that the temperature and the pressure are directly proportional. So what we mean by directly proportional is that if one goes up, the other goes up. If one goes down, the other goes down. If you were using temperature and pressure as arrows, they would be going the same direction every time, both in the same direction. So Charles's law, when you're calculating it, it involves either a change in temperature or volume. So T2 and V2 would be your changes. They would show up over here, right? And then your starting amount that you already know would be, T1, V1, and they're over here. So this is your starting point. And then this is your ending point, which shows that you had one volume at the beginning, one volume at the end, one temperature at the beginning, one temperature at the end. And if you've done any work with fractions, you'll know that if you're trying to get fractions that are equivalent, then you need to multiply both by the same factor. And we'll get into the factor in a little bit, but the factor is called a constant. And basically, if you pretended these were both numbers, like let's say this V is a 5 and this V is a 10. Well, then you've multiplied by 2 to get from 5 to 10. And so if this is a 10, what does this have to be? It has to be a 20, right? Because if 2 is our constant, then everything gets multiplied by 2 to go from the starting point to the ending point. So now when you talk about when the volume is constant, then we have to start thinking about temperature and pressure. And this is Gay-Lussac's law. So Gay-Lussac's law says that when the volume is constant, the temperature of the gas increases and then the pressure decreases. Increases. Pressure increases and temperature increases. And likewise, if temperature decreases, pressure decreases. So here's an Instapot, which some of you are probably familiar with. Once you put that lid on and seal this little knob right here, that means that your volume is not going to change, right? Your volume is constant. Well, as it heats up, the pressure is going to increase. And as long as you don't allow the volume to change, you keep this little knob closed and you keep the lid on, then you're going to build pressure. And the pressure and the temperature together actually help break down the proteins in the food faster, which is why your food cooks faster in a pressure cooker. And if you think about the temperature increasing and the volume not being able to change and the pressure increasing, there have been incidents in the past where people have used the old school pressure cookers, not the electric kind, but the kind that go on a stove. They have a locking lid, and they've used them to make bombs. And that's because if you put explosives inside, suddenly you're going to have a huge change in pressure and a huge change in temperature. And the pressure is going to build, the volume can't change, right? And the pressure is going to build so much because the temperature has increased so much that it actually explodes the whole device. So that actually changes your closed system into something totally different, right? So Charles's law, or Gay-Lussac's law, says that temperature and pressure are, again, directly proportional. One goes up, the other goes up. One goes down, the other goes down. So Gay-Lussac's law, if you're doing calculations using Gay-Lussac's law, they involve the change in either pressure or temperature from a known starting amount. So again, this is just like the equation for our last one for Charles's law. You have your starting pressure, starting temperature, your ending pressure, ending temperature. Exactly the same idea. Now, when the temperature is constant, we start talking about Boyle's law, or sometimes called Marriott's law. And this says that when the temperature of a gas is constant, if the pressure increases, the volume decreases. And then likewise, if the pressure is decreased, the volume increases. And a great example of this is thinking about taking the lid off of a soda bottle. So if you have a same, 2 soda bottles or whatever, the temperature is the same, it's the ambient temperature of the room, right? Your temperature is constant. If you decrease the volume, and you do that by taking, decrease the pressure, you do that by taking the lid off. So the lid's keeping the pressure in, right? And when you take the lid off, you've now allowed the pressure to decrease. So everything in here can kind of relax. And when you do that, the first thing you see is bubbles. And that is because the volume of your gas is now increased. It's the same number of particles, but now they're taking up more space, and you can see them in the form of bubbles. So Boyle's law says that volume and pressure are inversely proportional. So unlike directly proportional, in inversely proportional, if one goes up, the other goes down. If one goes down, the other goes up. So your arrows would be pointing in opposite directions. So Boyle's law in calculations looks different. So Boyle's law says that if you're involving a change in pressure and volume, you're starting with a P1 and a V1, and you're ending with a P2 and a V2. But in this case, we're not dividing, and it doesn't look like we're balancing fractions anymore. In this case, we're multiplying. And they will be inversely proportional. If one goes up, the other goes down. If one goes down, the other goes up. So when you put them all together, if you take Charles's law, which is right here, right, and Gay-Lussac's law, which is right here, and then Boyle's law, and you put them all together, you come up with something called the combined gas law, which you may use at some point. So it's good to know. And you can see how this works, right? We've got the V And the T's been on the bottom both times, see? And then your P and V have been on the top both times. So you end up with a mathematical expression that looks like that. So what's a constant? So we were talking about the constant before. So in this case, our constant, what is the number that we're multiplying both things by to keep them equal? And in this case, our constant we refer to as K. So sometimes you may see these equations or variations of these equations with the letter K. And K just means the constant. It's whatever you're multiplying V1 and T1 by to get V2 and T2. Or likewise with any of the other equations. So V divided by T is going to give you K. And P divided by T is going to give you K. In this case, P times V is going to give you K. And then over here, PV divided by T is going to give you K. So sometimes you'll see this variation of Charles' law, this variation of Gay-Lussac's law, this variation of Boyle's law, and this variation of the combined gas law. It's all the same. So what's the ideal gas law? So the ideal gas law is PV equals nRT. And an ideal gas is a conceptual approximation. This means it's made up, right? It's an approximate. It's a concept that we come up with that helps us model and predict the behavior of real gases. Gases are very different, so we can't always necessarily predict what a gas is going to do. So in order to have equations that function, we come up with this concept of an ideal gas. So ideal gas molecules do not attract or repel each other. These are the rules for our imaginary concept that we're going to use. And ideal gas molecules make them themselves take up no volume, which obviously is not possible, right? But you will use PV equals nRT, most definitely, at some point in chemistry, if not a lot. This go around, definitely in high school chemistry. So here are the answers from your notes. If temperature of a gas is constant, when the pressure is increased, the volume decreases. That is true. If the air pressure inside an inner tube is constant, when the temperature of the air is increased, the volume decreases, and that would be increases. There's a great example of this. If anybody has a vehicle in their family that has the tire pressure, the gauge on the dashboard that tells you when your tire pressure is low, sometimes at the very beginning of the fall or winter when you have your first really cold night and come out in the morning and get in that car, it reads low pressure. And that's because now you have decreased the temperature of the air inside that inner tube. The pressure has then decreased and the car's system recognizes that as a decrease in pressure and gives you an alert. The graph, I should have read first, the graph of the relationship between the volume of a gas at a constant temperature and its pressure is a curved line. And you will see another curved line in this week. Oh, I bumped it. Sorry. In this week's lab, actually. Or is it this week's lab? No, it's next week's lab. So if temperature and pressure of a gas inside a sealed rigid container is decreased, its pressure decreases. True. We're just talking about the tires, same kind of concept. The graph for Charles's law shows that volume of a gas at a constant pressure is inversely proportional to its temperature. Directly. Remember that Charles's law is directly proportional. If a gas at a constant temperature inside a cylinder topped by a movable piston is heated, the volume of the gas will increase and push the piston outward. This is true. This is how combustion engines work. So if you have a vehicle that runs on gasoline, this is exactly how this works, because there is a little spark and a tiny explosion in the bottom of the cylinder when the spark plug fires and gasoline is involved, and that causes a tiny explosion. And that causes the gas in the cylinder with the piston the volume of that gas is going to suddenly increase, and it pushes the piston up, and the series of pistons pushing up is what will turn the drive shaft, make the engine go, make the whole car move. So that's how a combustion engine functions. So thank goodness that's true, because I like cars. When the graph relating two variables is a straight line passing through the origin, the variables are directly proportional. According to what law? According to Boyle's law. When the pressure of a gas at a constant temperature is increased, the volume of the gas decreases. Remember, Boyle's law is the one that is inversely proportional. According to which law? Charles's law. When the temperature of a gas is increased at a constant pressure, its volume increases. And when the product of two variables is constant, the variables are what? Inversely proportional to each other. So here's your clue. It says product. So product, remember, is the answer to a multiplication problem. So if you see product and you know it's being multiplied and not divided, it's got to be Boyle's, because it's got to be Boyle's law, because it's got to be inversely proportional. Because remember, the others are all divided and they are directly proportional. So now what you need to do is go back to the assignment in Teacher Ease, and you should be able, I believe, to open the discussion and enter a description of one of the images you saw. And if you have any questions, go ahead and leave them there. Be sure that you take last week's homework, if you haven't already done so, and upload it in PDF format to the assignment in Teacher Ease as well. And then I think that's good. Go to the lab, watch the lab video, and upload that written lab report also as a PDF to that assignment. Okay, so hopefully I'll see you guys next week. Let's all pray we get back to normal soon. Bye.